Hello, everyone. Welcome to ROS Industrial EU Conference 2020, the virtual edition. I am Tejas Kumar Shasta. I'm a research associate at Fraunhofer IPA in Stuttgart, and I will be the host of this session today, which is titled Industrial Tools and we have four speakers lined up in this block in this session with about 15 minutes allocated to each speaker. And at the end of 60 minutes, we then have another 15 minutes time where we can take questions from SwapCard and also look at some of the polls that are in SwapCard already. So I suggest all the viewers who are looking into the stream now to actually post some questions that you have there and also to take part in the poll and register what your feedback is. With that, I welcome all of the four speakers and all of the viewers who have tuned into the stream, and I also thank Christoph, my colleague, who's taking care of the streaming service to make sure everything's fine. One thing I do want to inform everyone is that there is about 15 seconds lag between the live event as well as the stream that you see on SwapCard. So if you do post some questions there, it might take us some time to actually react to it. So now I would like to invite our first speaker, Johannes Meyer. To introduce him shortly, he's presenting from Leuven in Belgium. He graduated from the University of Karlsruhe in 2008, and he joined TU Darmstadt there as a researcher. He has been with Intermodalics since 2013, where he works now as a lead developer and architect. Intermodalics itself is a robotic software development company. They help with complete product development lifecycle in robotics. And they are experts in visual positioning systems, machine vision, navigation control, and more. Johannes will now be presenting his topic of Orocos, the real-time toolkit. Johannes, the mic is now yours.
Okay, so thank you for the introduction. I hope it's okay with the audio and the presentation. Yeah, so my name is Johannes Meyer. I'm happy to present today Orocos, or especially the real-time toolkit of Orocos. So this is how the presentation is structured. So the first question is already answered here. What is Orocos? It's the open robot control software. Give a brief overview of the history of Orocos and what it can do for you, what is real-time, and introduce it. And in the second part of the presentation, explain how it maps to concepts in ROS and how it integrates. On the right side, you see some applications. So on the top, there are some drone applications. That's how I started to work with Orocos back at Darmstadt. And then also as a first project, we controlled a fleet of drones in a French theme park using Orocos on board. There are also industrial applications, and until today, we support NASA and other companies with Orocos. Use Orocos, and we use it, of course, for our own product in industrial bin picking application. So the three pillars of Orocos, so it's basically a collection of libraries and toolkits. Today I'm going to talk about the real-time toolkit, but you might know KDL, Kinematics and Dynamics library, which was also developed for this project, and the Bayesian filtering library, which is not that much used nowadays as far as I know. But KDL and real-time toolkit are still actively used by the robotics and especially also the ROS community. Brief history. So Intermodalics, the company I'm working for, actually started more or less as a support or as a consulting company for Orocos. Originally, the project was started at KU Leuven together with partners in last France and KTH in Stockholm in 2001. First release was then in 2005. 2010, there was like a major upgrade financed by PAL Robotics, I guess. And today we're working towards 2.10, so we're more in maintenance mode than adding many new features, but we are using it for our own projects. As you can see, it's actually predates ROS, so it's more like the grandfather of robotic frameworks, especially that, or at least in the real-time context. Yeah, there are many projects and funding from industry, and there's also still an ongoing project funded by ROS, especially about the integration with ROS2. So what is a real-time system, or in other words, why you might need Orocos on top of something like ROS? So on the first, a real-time system has to be deterministic, always produce the same output for known input. You need to meet finite time windows, so meet deadlines for which a certain task must be completed. That puts many restrictions on the user code and on the system. And of course, there are different requirements. Not every real-time system is the same. In some cases, there are less restrictions than others. But let's say most control requirements, you have some real-time requirements, most control tasks. It's not only about the software. So overall, of course, you need to also consider the real-time computer. Most CPUs can, in principle, run real-time code. But we have to communicate with devices, robots, and hardware. So all of those things have to be considered to actually make a real-time system. And Orocos is mainly so it's not an application itself, but it helps users to develop real-time safe code in a component-based framework. Not much different from ROS, but yeah, with real-time in mind as the first class requirement. So how does it work? The core concept is a component. It's a component-based framework which unites all the functionality, very similar to a node or notepad. Components run in principle single-threaded. Only you have multiple components and multiple threads in the application. And the component is basically a container for data flow ports to communicate data from one component to another. Similar to ROS topics, operations, which map basically to ROS services. So they call functions with a response. Can be called synchronously, asynchronously. There are properties to configure the component, for example, controller gains. And you can implement the actual functionality in books in C++ or using custom scripting language. Also Lua is possible, and it supports state machines and program scripts via plugins, so it's not a must. And it's all tailored towards real-time safe interaction of these components primarily through the data flow. It's possible to extend it through plugins, like for example, the scripting is one of the plugins, or to provide common interfaces, for example, for PID controllers. The components have a life cycle, like also nowadays most tools. I won't go into much details here. The component can be running or stopped. It does not necessarily have a pre-operational state. And if anything goes wrong, if there are any errors, for example, hardware malfunction, the component can also signal that to other components by going to an exception state. So that's very much like ROS nodes today. But Orocos is essential. Orocos there from the ground up. Most important is the data flow. It can be configured in a highly flexible way, depending on the requirements of the application. So there are no topics, like everyone listens and subscribes that support the same topics, but it's end-to-end. So every output port is connected to an input port individually, and every connection can be configured and requirements. So one of the configuration options are, for example, whether it's data connection with a single element or buffer, whether it's locked using mutexes or lock-free. The default is lock-free. There are pre-allocated buffers. That means you can set a sample size, and writing and reading from the port is in principle real-time safe. And also here, the data flow can be extended by transport plugins. For example, ROS interaction with the transport plugin to not only connect components with each other, but also to the outside world. Last but not least, there's the Orocos deployer, which is actually the Orocos component library, so it's already an add-on package. And once you have written all the components, or for example, hardware drivers, controllers, and so on, you have the possibility to either write that all in a simple monolithic application, executable to compile that, or describe the deployment in an XML file or in an Orocos script that then explains which components to load, can import them from packages, configure them, configure the threading, the connections, and at the end runs the application in a real-time context.
Johannes, if I could interrupt you briefly, we have some feedback on Swapcard that your audio is not completely clear. Would it be possible that you switch to another device?
Check. I'll try to speak up a bit. Maybe it's better. Okay. I got a bit closer and I'll try to speak up. So this is, in summary, how the concepts of Orocos map to existing concepts that you might know from ROS. So a few things are different. In ROS, you typically have some spinner threads or executors, and they call callbacks. In Orocos, a component has to actively read from an input port, but an input port can be also an event port optionally, and then the component's woken up in case there is a new event and someone wrote to that port. In general, every type that, for example, KDL frames can be used on ports and for operations, so it's not restricted to certain messages and services, and you don't have to convert those types. But in order to use them in Orocos, you need to generate a type kit that explains your type basically, and in essence, if it's a struct type, how to access certain fields, for example. There's a mismatch between the concepts of an operation. So an Orocos operation matches more what in services and ROS. So it's basically a function call, also more general in Orocos than in ROS. And what in Orocos is a service, that's more like what a plugin can provide. There is no direct match in ROS, but it's more like a namespace which has common topics. For example, like dynamic reconfigure, which expects certain topics in the same namespace. Other concepts more or less match exactly. You could directly compare them to each other. So now, how does that all integrate with ROS? So already in 2010, Ruben Smits, my colleague, worked on the RTT ROS integration to integrate it. And already since then, there are some packages. Later has been extended by more contributors. There's RTT ROS, which is the basic package to import ROS packages, which provide component libraries or service plugins or type kits and launch files to actually launch Orocos in a bigger ROS application, which is often the case that Orocos does not run standalone, but nowadays you can run it in combination with ROS for the non-real-time parts. RTT ROS node provides a service plugin to instantiate the ROS node, and then RTT ROS-COM is the package where that you can use to generate type kits for existing ROS messages and services, and to transport plugins to actually connect to the topic, to the ROS topics. RTT ROS-Param has helper functions and service to synchronize RTT properties with parameters, and RTT TF allows to interact with the TF system to look up transforms, not real-time safe, but to publish TF transforms in a real-time safe way, which is the most common application of it. And there's also an implementation of an action server. There are some other packages that I won't mention here, but it's also possible to have RTT properties dynamically reconfigured or to interact with the clock system, for example, in running a simulation. Since this year, so it's still under development, we have a basic implementation for ROS-2 ready. The structure is very similar. The RTT ROS-COM package has been split a bit, and we use the nomenclature of ROS-2, which would mean there's a package called RTT ROS-2 interfaces, which allows for any interface package in ROS-2 to first generate a type kit. There are some applications where you only want to generate a type kit, where you don't need to interact with ROS directly. We use these types internally only. ROS topics, which provides the transport plugins for the Orocos data flow, and ROS-2 services to interact with ROS services, to both call ROS services in a real-time context, most of the time asynchronously, and operation callers, which allow to call ROS services. RTT ROS-2 params then sync the parameter, the properties of an Orocos component with the ROS-2 parameters. So primarily, if ROS launch, for example, was used to configure, then you can get parameters from there using this package. We're actively working on TF2 support or TF support for ROS2, and also integrate actions to make it in general more seamless interact with ROS2 systems. The documentation is available at the old webpage, www.orocos.org, but now it serves more as a landing page to serve some of the legacy documentation, and also as a big work pattern milestone of the ROS End project. We centralized the documentation of this new page. You also see at the bottom here. So that's like the best entry point to start looking at Orocos. It's hosted on GitHub, so everyone can contribute. There are tutorials and examples, partially new, partially gathered from other locations that have been distributed over the years, and also especially on the RTT ROS integration, make some new tutorials. So to conclude, Orocos is a bit older than ROS, but it started with a strong focus on real-time applications, which we heard this morning from Christoph, that especially industrial application is a kind of requirement, or many companies ask for that. In its core, it's RTT and the component library, which you can consider as part or an extension of RTT, but also KDL and BFL might be of interest and unrelated to that. And with the help of the ROS integration that already exists and also exists for ROS2, it's actually possible to combine Orocos applications for the real-time part with other ROS applications, primarily for visualizations or to integrate with other parts of the ROS ecosystem. So planners, for example, that don't necessarily have to run in real time. Short summary on the current status. So a new version will be released soon. There was a lot of development activity in the recent 2-3 years, but it's not yet polished to publish. So very soon we will release the newest version to 10 into the current ROS distributions. The basic ROS2 integration is also available since this year, and you're welcome to check out the new documentation at docs.orocos.org if you're interested and want to have a further look and learn about how you can use Orocos for your application. Thank you very much, and I'm looking forward to your question at the end of this session.
Okay, thank you very much, Johannes. If some part of the stream was not perfectly clear, and if the viewers would like to go through some of these slides again, maybe you could mention this as a question, and we could take it up during the discussion session again, where Johannes could possibly repeat these topics. Thank you. So our next speaker is Rafael Arrais. He is joining us from Porto in Portugal. He completed his master's studies in the University of Porto, and he has been for 6 years with INESC Tech as a researcher, and he currently works as a project manager. He's also a PhD candidate at the University of Porto as well. INESC Tech is an associate laboratory with 35 years of research experience with over 700 employees spread over 13 centers in 6 cities in Portugal. And they act as an interface between academy, industry, and public administration in the fields of IT, telecommunication, and electronics. Rafael, thank you very much for joining us. And now the microphone is yours.
So thanks very much, Tejas, for the introduction. Thanks also very much for the opportunity to speak at this event. So I had the opportunity to also address this issue or this topic last year, and this year is a pleasure to come back to present the final results of this project. This ROS-Codesys bridge that I'm going to present today was developed on the scope of the ROS-I initiative. So it was an FTP of the ROS-I project, and right now we are pretty much concluding the project and presenting its final results. Before addressing what we developed to bridge the automation and the robotics world, just a mention of INESC Tech and some of our initiatives and also our projects. We've been developing in the last couple of years since the FP7 European project frame. We have been focused a lot on mobile manipulators, specifically for the automotive and aerospace sectors. We had the opportunity also to put in place and to test out this bridging mechanism between robotics and automation in several demonstrations for the end users that compose our final demonstrators of our projects, ranging from the PSA group to Renault to Embraer. So we had the opportunity to assess these kind of technologies in field, which is also very important when we are addressing an industrial forum such as the one today. Focusing now on the scope of the presentation. So as I mentioned in the beginning, the objective for this development was to provide a way to easily bridge the automation and the robotics world. So in other words, what we are trying to achieve is to use a soft PLC, in this instance CODESYS, to act as a communication bridge between to the automation world, so to field buses and devices that not necessarily speak the language, which could be easily understood by ROS, but nevertheless, through the usage of such a tool, we aim to reduce the effort needed to make a communication and an integration between automation and robotics. So this concept is based on the usage of an embedded device. So we are basically taking advantage of the fact that the novel embedded devices available on the market can run Linux environments, and in this instance, the device that we are using, which is a BeagleBone Black, can run an instance of Ubuntu, which makes easy not only the installation of ROS on one hand, but also on the other hand, the installation of CODESYS, because the company that provides CODESYS already has published a version working for the Ubuntu distribution of Linux. And also picking up on the fact that the CODESYS that BeagleBone Black, can provide a real-time communication approach to devices. It makes it the suitable candidate for trying to achieve such a communication infrastructure. The way that this works is summarized here on the left side, on the right side of the slide, where we have our high-level architectural overview. The idea is that a ROS node communicates with the CODESYS application through a shared memory approach. Shared memory is then controlled. The access to the shared memory is controlled by semaphore-based control mechanism. And on the ROS point of view, the information that is written or accessed or on this shared memory is made available to the system through the usage of ROS topic, as it will be apparent in a few slides. So to actually accomplish this mapping between the CODESYS domain to the ROS domain, we had first to look at message conversion. So in other words, we had to look at all the message primitives on the ROS ecosystem, look at what they meant in terms of their internal representation in C++ in this instance, and then think on how we should convert them to a message typology compatible with the one which CODESYS uses, which is based on the IEC norm for the automation world. In the last year, I mentioned that we were working on this conversion and trying to get this established. Right now, we have all the data available and fully supported by our implementation. The only limitation is the fact that a ROS string needs to be mapped to a fixed length array that is nevertheless configured by the user, but these strings have to be of a fixed size due to the restrictions of the conversion. But nevertheless, the conversion of the messages are now fully working in our systems. Quickly looking at how we implemented this on the ROS domain. So on this slide showcases the class that we implemented for Robin, or the ROS-Codesys bridge. As I mentioned before, the information for the ROS ecosystem is made available to a topic-based approach. So in other words, we have defined several methods to access, write, or read the shared memory, and then automatically either publish this information to a topic or subscribe to a content of a topic, use it to write to this shared memory location. From the point of view of the developer, the usage of this system is very simple, and we have provided several ways for developers to instantiate this system in their own programs and applications. The quickest way or the simplest way is to just include this Robin class or library in their C++ code, and basically create 2 instances of this class to either write or read the data to the shared memory. Nevertheless, because we thought that this could be simplified, what we also developed, and I will focus this on the following slide, is an interface to automatically generate this infrastructure. But before we look at that, looking a little bit on the Codesys side. So what we have developed is a project structure which already hosts most of the data structures that ROS messages take part or are composed of. So in other words, what we have done is mapped all of the standard messengers, sensor messengers, and so on, which is fairly common in ROS transactions. We map them to a Codesys structure which is given with the tool, and we also enable developers to create their own custom messages structures. This way, what the developers can do on the automation side is to simply use these structures to construct their own variables and then instantiate their own variables into their own programs, which can be written in their language of choice, so ST, ladder, and so on. What I was mentioning in a couple of seconds ago was that we created a simplified way to basically instantiate or create the infrastructure on the ROS system. So if we assume that the Codesys project or the automation project is already created, we have developed a Python-based script that basically has a look at all the variables used on the Codesys side, checks their structure, so checks which kind of message in the ROS system they refer to, and then through this Python-based script, what is being done is we trigger an automatic generation of the code infrastructure on the ROS system. So this is what hopefully is being shown on the screen right now. And having this interface created, what we have to do is to simply rely on a publisher or a subscriber. In this instance, we are subscribing information from the automation domain, and we are seeing the changes that we are propagating on the Codesys side being mapped to the ROS, to a ROS topic that is then available to the full ecosystem. On top of that, one innovation that we added in the last, in this year, in the first months of this year, was an automatic code generation tool to basically simplify the life of the developer. So in other words, the developers can use this approach to generate an instance of a template using a YAML file with a syntax similar to the one that I'm showing on the left side of the slide, to generate a PLC open compliant XML structure that can then be later imported to Codesys, to their projects in Codesys or even on other automation applications. And this, we hope that this can even simplify further the establishment of this initial infrastructure for communication between ROS and automation devices. Finally, to conclude, I have here a video showcasing the final results of the scalable project, where we have demonstrated the usage of this tool in supporting 2 very important parts of the final demonstrator. So on the left part of the slide, I have a schematic showcasing how we use this ROS-Codesys bridging communication to make the interface between ROS master application, which was running on the robot level, with the conveyor, which in this demonstration basically was responsible for sensing different tools arriving from injection machines and notifying the robot that these components were suitable to be picked and packed. And on the right side of the slide, I also have the communication infrastructure that basically allows us, or the ROS master in this case, to directly communicate with the manipulator controller to actually instantiate the controller to perform its task. So I invite you all to check out the results of the project, not only on this video, but also on the links of this YouTube page to check out also the other innovations that we have conducted on the scope of this research initiative. Finally, my very last slide, just to conclude what was presented here, what was condensed to this presentation. I would just want to raise the attention that everything that I mentioned here is, of course, explained in more detail on our GitHub page for the Robin project. In there, you can also find, of course, the source code to everything to use the Robin in your own project, but also a detailed README and guide to getting started into communicating between robots and automation devices. And for the ones interested in a little bit more in the science behind all of these and what made this kind of communication feasible and possible, I also advise you to check out the paper, the journal paper that we published a few months back, which details pretty much all that I presented in a scientific way. And well, this concludes the presentation from my side. I'm looking forward to your questions also in the final part of this session. Thanks.
Okay, thank you very much, Rafael. I would like to remind all the viewers that we will, of course, be uploading all of these slides and this video as well, and you will be able to shortly follow up on these links as well. Thank you. So our next speaker is Luca Muratore. He's joining us from Pisa in Italy. He completed his master's studies in the University of Madrid, and he has been for 6 years with Istituto Italiano di Tecnologia in the Humanoid and Human-Centered Mechatronics department, where he works as a lead software engineer. He also completed his PhD recently in 2020, so congratulations, Dr. Muratore. Thank you for joining us. This microphone is now yours.
Okay. Can you hear me? Yes. Okay. I will share my video. Okay, thanks a lot for the introduction, and today I'm going to present to you the results of the ROS End Effector, which was a focused technical project of the ROS Industrial, funded by the ROS Industrial, and this project was carried out in the Humanoids and Human-Centered Mechatronics department at IIT, as you said before. This department is led by Nikos Zagaragis, and we will start to understand the motivation behind the ROS End Effector. So the idea here is that robotic end effector complexity is growing more and more during the last years, together with their adaptability to different tasks. One of the major issues that we notice is the integration in research and industrial scenarios that usually requires tailor-made software or custom modules developed from scratch. For sure, this is not going to work, and really we have a big gap between the lab and the industry scenario, where we don't have really generic software to reuse and to speed up this integration process. In the slides, in the, let's say, bottom of the slide, I'm trying to show to you different end effector with different number of actuators, different kinematics, and in general, different field bus. So you will see the RE2 ends that was actually developed in our department. It has 4 actuators with 4 fingers. We have the robotic 3-finger ends, gripper style with 3 fingers. The Q piece of stand that is peculiar because it has only 1 actuator, and actually it used the concept of synergy for a tendon drive mechanism to open and close the hand. Then we have a simpler gripper, the robotic 2-finger 140, or the shunt head that actually has 9 actuators, so pretty complex anthropomorphic hand. The issue here is that each of these hands needs specific software, and what we try to achieve is the main goal of the ROS End Effector that is described in this slide. That is to provide the industrial and research communities with an open source, first of all, plug and play and hardware agnostic control framework adaptable to a large variety of robotic end effector. And for sure, we use ROS as the, let's say, main communication layer and main, let's say, software platform that is the de facto standard in the research community. The concept that is the core of the ROS End Effector is the grasping action concept. What is a grasping action? This is a particular end effector pose. That means a particular set of actuator position. A primitive grasping action can be seen as an atomic motion of one or more fingers. It is defined by a name, which records the function of the primitive, and the key, which indicates the elements that are involved in the primitives. One example can be a pinch, that is a precise grasp that is done with 2 fingers, for example, thumb and index. In this table, I try to recap a bit the primitives that we list based on the state of the art. So we try to figure out which were these atomic motion of the end effector. And we have, for example, the trig, the tip flex, and the fin flex. These are motion related with 1 fingers. And for example, the trigger can use 1 or more actuator, as you can see in the table. We have description and we have some constraints. For example, the trig, at least 1 actuator that moves only 1 finger. Then we have a set of pinches, as you can see here, pinch tight or pinch loose. This is a small difference because we use 2 fingers, but in the tight case, we have collision between the 2. In the loose case, we don't have it. The multi-pinch is a pinch done with more than 2 fingers. And then we have a single joint multiple tips. That means that 1 actuator moves more than 1 finger, but probably it's gonna be more clear with this video example. You see here some trigs. On the left, you see an index trig, on the right, middle trig. In the simulation, we use the shunk end in RV, so we have kinematic simulation because we don't have dynamic parameters of the shunk end, but we will see that ROS End Effector provides also built-in support for gazebo simulation. Again, with the shunk end, you will see an example of the pinch tight on the left, where thumb and index actually collide, and the pinch loose on the right with index and little. Then on the left, again, the shunk end with the single joint multiple tips motion for the thumb opposition, and the single joint multiple tips is pretty clear in the right, where you can see the soft end that actually has only 1 actuator that closes all the fingers. For sure, the user can define his own custom grasping action because the primitives sometimes are not sufficient. So the ROS End Effector API provides the user with this possibility. And in this case, we build up a custom grasping action based on 4 trigs that are summed together. So trig for the index, the middle, the ring, and the little show this kind of behavior on the hand. Let's mention now some details about the software architecture. We have 2 different phases, the offline phases and the online phases. We are going to go in deep and try to understand the difference between the 2. So in the offline phases, we have the ROS End Effector primitive extractor as a main node. What the user that want to control his end effector needs to do here is just to provide 2 configuration files, URDF and SRDF. What the framework will do is to automatically extract the primitive grasping action based on the end effector the operator, the user, gives to the framework. So how this phase works, basically we have implemented an algorithm based on collision checking that is exploited to find the pinches, and then the other primitives are found using the robot kinematic tree. The output of this phase is a set of YAML file that actually lists all the available grasping action. For sure, through the ROS End Effector API, we can add some custom action, as we saw. And it's worth to mention that the offline phase has to be run only once per end effector. So once we define URDF and SRDF, we don't have to run this phase again. The online phases is used to command the end effector to go to a certain, let's say, grasping configuration. The main node here is called the ROS End Effector grasping action executor that is actually used to parse all the grasping action and use them to actually control the end effector. So it takes as an input the grasping action YAML file and also URDF and SRDF, and is capable to receive command by means of ROS action that are grasping action commands. The framework actually provides the ROS End Effector GUI, a built-in graphical user interface to control the end effector. And for sure, this GUI that is equity-based is dynamic. So as you will see later, the GUI behavior and layout will change based on the primitives available for this end effector. One of the main components of the framework to achieve the goal that we actually discussed before is the ROS End Effector hardware abstraction layer. This is fully integrated in the ROS End Effector, and we actually have this abstraction to generalize the way the states and the reference are received and send to the end effector. So we implemented some, let's say, real end use cases like the end-to-end or the soft end. Then for sure, the user can implement the hardware abstraction layer for his own gripper. It's very simple. You just need to provide some getter and setter to communicate with the field bus that the gripper or the end effector in general uses. And moreover, the framework provides full support for RV simulation, so kinematic simulation, and gazebo simulation. So we actually provide the user with a plugin that is capable to simulate with gazebo your end effector. Let's take a look at the GUI, so how it looks like. We have in this case a GUI that is dynamically built up for the end-to-end. We have some of the primitives here. You can select the finger that is the key of the primitive grasping action, and you can actually send the action. For sure, on the right, you have all the list of joints, active, passive, mimic, and you can understand what's going on in your end effector. We have another tab that is actually more specific to the state of the end effector. Here, as you can see, you can select the joint, you can plot position, velocity, and effort. This is all integrated in the GUI, and the green stuff you see here indicate that the joint does not have faults or error. Let's try to understand how the user can command a primitive through the GUI. So we take a look at this example here. We have the grasping action name. Then we have the feedback about the action completion. We have a selectable fingers for this specific action. The trig needs only one finger. So for example, we select just the index. And then an important value to set is the percentage to scale the motor position go for the action. For example, in this case, we commanded the 75% and then we opened the end at 0%. Let's speak about the experimental results. This is probably the most interesting part because we were able to demonstrate the capabilities of the framework, both in the simulation, again, kinematic simulation with the Shunkan that is pretty complex. So we have a lot of primitives that are generated, and you will see the results in the GUI. In Gazebo, where we have also dynamic simulation with the robotics and effector, and also with the QB soft end, but most of all in the real hardware, let's say, use case scenario with the end-to-end. Here you see how the GUI looks like for the Shunkan. You see also some custom action defined there, but you see that we are able through the ROS End Effector main executor node to command the primitive and to receive, let's say, the feedback about action completion. And in our video, you see the hand moving. Let's say we have a new hand that is the robotic 3-finger. What we need to provide is just URDF and SRDF. And again, the GUI is automatically built up and we can control the primitives that are available based on the offline phase. This is a simpler gripper, the robotic 2 fingers, but again, we have some primitives that is the pinch tight or the single joint multiple tips that is gonna lead to the same movement. The QB soft end that actually has a single joint multiple tips again here to control the end. And in this case, for the robotics, we are in Gazebo, so we have the simulation for the dynamics of the end. And the experiment on the real hardware has been conducted on the Harry-to-End, that is a prototype developed in our department. Here, I just stopped the video to introduce to you a time grasping action that is a special action that is actually composed by inner action that will be executed one after the other in a certain time frame. So we want to actually control a drill. So what we need to do is to use this 3-finger motion to actually hold the drill. Then we can use the trig motion to activate the drill. And then we should stop, let's say, with the trigger off to stop the drilling. You can see on top all the states of the robot and the joints of the robot that are actually updated in real time. Let's wrap up with the conclusion and some of the future work. What we present today is the ROS-based hardware agnostic control framework for a large variety of end effector. The ROS End Effector revolves around the concept of primitive grasping action that are automatically extracted from the robotic end effector model information that are URDF and SRDF. The hardware abstraction layer helps to communicate with the robot and is actually used to abstract all the low-level details of the end effector. It will soon be integrated with the Crossbow 2 framework that is a real-time cross-robot and cross-framework software architecture that will permit to us to control a whole, let's say, system, both using real-time controller and no real-time controller. In this case, the end effector is, the ROS End Effector is still using the ROS-1. We are working on the ROS-2 integration, but the main work today is focused on the ROS End Effector graph planner that, as you can see today, we have the GUI to control manually the hand, but what we want to do is to compose primitive grasping action together to allow the end effector to grasp an object in a complete automatic manner. So further information can be found in the DVR Humanoids ROS End Effector repository, where you can see all the source code. The documentation is at the link here, and we have also a video presentation. So I thank you for your attention. I would like to thank also the ROS End Effector teams composed by Davide Torrielli, Liana Bertoni, and Nikos Zagaragis. Without them, the project will not succeed. So thanks a lot, and thanks for the presentation to ROS Industria.
Okay, thank you very much, Luca. That was a very interesting presentation. Perhaps my colleagues and I would like to try this out next week. So our next presenter is Alejandro Mosteo. He's joining us from Zaragoza, Spain. He has completed his PhD in 2010 in the Centro Universitario de la Defensa in Zaragoza, where he is now working as a professor in the same university. His current research interests include distributed algorithms, flying robots, augmented and virtual reality, and machine learning. He's very much interested in Ada, the language, and an interesting side note, he's also a composer and a chorus. Thank you very much for joining us, Alejandro. The microphone is yours.
Thank you very much. Thank you for the nice presentation and for having me here today. So I'm going to talk about the Ada client library for ROS-2, and that could be the summary of my presentation, that there is a maintained client layer for ROS-2 in Ada and by extension for Spark, not this Spark. I will talk about Spark a little more in a few moments. So I'm starting from the assumption that most people is not very familiar with Ada, if at all. So I will devote first part of the presentation to doing a bit of advocating of why Ada is a good match for robotics and for ROS-2. And then I will address a few particulars of the library a bit more in detail. So just so you can see the kind of research I'm involved with, I belong to the Robotics and Real-Time and Perception group of the University of Zaragoza. And we do research in autonomous exploration in underground scenarios. At the moment, all of our robots run ROS-1, but we are aware that at some point in the future we will have to migrate to ROS-2. And speaking of robotics in context of academia and industry, of course we have many points of overlap, but in industry there are some aspects that are critical. The robots may have to run for a long time, and they have to adhere to some certification. And of course, correctness is of the utmost importance in all cases, unless you want to make headlines like this one, for example. And I know that there is Ada in Boeing planes, but I don't know if it's related to this particular problem. When you have to develop for high integrity systems, and I think that autonomous robots or autonomous vehicles will be ever more present in our society, you have at least two ways. One is to take general purpose language and remove everything that makes it unsuitable, or you can start with a language that was designed from the start to address this kind of systems. Just a quick trip down memory lane for Ada. It was commissioned by the Ministry of Defense, Department of Defense, because they had a lot of languages and they had a maintenance problem with this. And so for this kind of critical systems, they started a competition. The winner was a proposal that was finally renamed to Ada, that later became a standard and was mandatory for a few years in this context. And that has survived until today in a niche, but several niches which are very important, I should say. So that's why ADA stays relevant, and it's a good match for the kind of applications that are being done right now in robotics. It's a language that has evolved with the years. It's modern in its latest iterations. It's very well documented both for compiler writers, for users. We have the Bible in the reference manual where everything is explained in excruciating detail. And also compilers have to pass a suite of tests if they want to claim that they are ADA compilers. And well, ADA is a kind of spiritual successor to Pascal, so the code looks similar and it has all the features you can expect from a mature language. But for me, there are a few that are particularly interesting when doing robotics, which is the support for high-level concurrency, and also the design by contract characteristics that allow to write pre and post conditions, and also type invariants and things like that. Since ROS2 was started also to address some shortcomings of ROS, in particular for high integrity systems that require to address this kind of problems with real-time execution. And the thing is that this is actually what ADA was made for. So with ADA, you can go from the lowest level to the highest level in a portable way, and you have specific features to support your development of high real time in a portable way. And also it's used in this kind of industries where certification is important, and there are ADA tool chains that you can use for this kind of development. So an example of this, for example, is ROS2 allocators, which were introduced to control the way of allocating memory, which can be a source of indeterminism. And in ADA, this is done. Well, this existed in ADA since the beginning with storage pools. And for example, in the ADA library, this is mapped directly to ROS2 allocators, which means that for ADA developers, they have to do nothing because they are transparently using ROS2 allocators. And this is a feature that allowed me, for example, to verify that the C client layer in ROS2 indeed is free of memory leaks, for example, by using the ADA storage pools devoted to debugging. And in this kind of memory concerns, for example, ADA has many ways to control dynamic allocation, from forbidding it internally to allowing it during initialization, or redefining how this is performed with deterministic algorithms. This, which can seem a hard constraint, in ADA is not so much of a problem because many things that require dynamic memory in other languages can be done in the stack. You can have types with unknown size, but as long, well, of course, the values at runtime will have a known size, and this allows the ADA compilers to allocate most things, many things that in other languages use the heap in the stack. And for example, this allowed me with relatively little effort to make the ADA client library for ROS free of heap allocations. Everything is allocated in the stack. And then there is Spark ADA, which for the most stringent needs is the part of the language, is a subset of the language. So the same compiler is used to compile, which is in this very, very convenient. It's the part that relays on the contracts on the code to verify properties of the code. Not only these properties can be asserted at runtime, but you can prove from absence of exceptions to particular properties of critical code sections, or if time and budget permits, all of your program. Well, it's a technology that doesn't need to go full in with it. You can adopt it incrementally. And so in this is in some regards similar to targets the same objectives of RAMA and ROS-I. with the difference that ADA has less undefined behaviors, and you don't have to learn a new specific syntax because you are using ADA syntax. This is just a recent story about Spark for those interested in it, so you have a thread to continue pulling from it. And now moving on in particulars of the ADA client library, I will talk about 3 aspects of it. First, what's the source code organization, then how this is built, and finally, how a few details about the client, about the API of the library. So the sources are organized and they are at the same level as other client libraries. So we have the client library that relies on the C client library, and then on top there is the user code, in this case written in ADA. And well, basically we have at the bottom of the stack the ADA tools. Then we have a few ROS2 packages that provide the client library proper. And finally, we also ship some examples, the typical client library examples for the library. In regard to how to build your code and the library code, this is done using the standard Colcon CMake target format. And to simplify the life for ADA programmers, what we do is to provide a few extra CMake functions that once you import the common section of the library you have available to start an ADA package, to import the rest of the library, and if you need messages from other nodes, also to import those messages, and declare your own executables or libraries for the use within the ROS2 ecosystem. And finally, export the environment to other dependent packages. Finally, in regard to the API proper, which is the core of the library, of course, this is a binding in the end. So there is the choice between making a thin binding or making a thick binding. So, So in this case, we leverage the characteristics of the ADA compiler that is able to generate bindings from C headers. So this allows us to leverage the best parts of both worlds, of thin and thick bindings. The first time that you compile the library, a thin binding is generated automatically, which of course is up to date with the C headers. And then on top of this one, there is a thick binding, which is manually written and which is the one that's intended for use of the developers. And of course, any mismatch there will be detected at compilation time instead of getting mysterious failures or segmentation faults if some function has changed in the underlying C library. So this is properly detected. As I said, this is of course, the user code could use this thin binding if desired, but the idea is to use the thick binding. As for the latest developments in the project in this year, we have the porting of the library, making it up to date to both Dashing and Foxy releases of ROS2. Continuous integration has been implemented at this time in the GitHub Actions, although the idea is to at some point have it with the ROS2 build farm. And finally, the library is also integrated with the ADA package manager. So for ADA users, it's super simple to deploy and start developing with ROS2 and with ADA. There are a few bits of the client library still to be included. I hope to include them very soon, which is, for example, the parts devoted to actions. Finally, in conclusion, of course, the main idea is that there is an ADA client library for ROS2, but also this library has some distinguishing features like, as I said, there is no dynamic memory allocation. It's auto-generated in part from the C headers, so there is no risk of becoming silently outdated. And being ADA, you get all the benefits of the language that were conceived for the development of high integrity systems, which very good compatibility, not only backwards compatibility, but also when you change cross targets or development platforms. The worst thing that can happen is that the compiler tells you that the architecture doesn't support some features that you think you could use. And also, it's very simple to call C or C++ from ADA, so if you want to drop back to C or C++ for some parts of your code, there is no problem in doing that. So this is the end of the presentation. Thank you.
Okay, thank you very much, Alejandro, for that interesting presentation. We are right on time, actually. I would now request all the presenters to switch on their video so that we can go into gallery mode for the panel discussion. You could still stay muted until perhaps we start addressing questions directed towards you. So if I look at some of the questions that have already been posted, there are actually already 2 questions for you, Johannes. Anis asks, ROS2 already handles real-time constraints, right? So why should one use Orocos with ROS2? His understanding was that you either use ROS1 plus Orocos or you just simply use ROS2.
Yes, so it's a good question. So of course, yeah, Orocos started much earlier than ROS. To be honest, I'm not 100% sure about the latest development. I know that Prosima and also Bosch has been working hard on making ROS2 really real-time capable. I think, yeah, there's still, like, at least at the time when we started looking into it, and like 2 years ago into ROS2, there were a lot of good ideas and APIs to fully support real-time, but it was not as powerful yet as Orocos used to be. So, for example, in setting up data flow, Orocos offers quite some flexibility in configuring the connections to control which component runs at what time, what callbacks execute at what time. A component can be a slave of another component, for example, such that the hooks don't run unless it's explicitly executed and so on. So, yeah. I think that's still not comparable to what ROS2 can do, but I'm looking forward to the talk tomorrow to also hear from the latest developments on the ROS2 side. One of the goals, of course, to integrate it with ROS2 was also to be able to reuse Orocos components with ROS more seamlessly, so that basically they can just coexist and you can just spawn an application with ROS2 nodes on one and Orocos components for other parts of the system.
Okay, thank you, Johannes. I suppose we look forward tomorrow to shed some more light on this question. We actually have another question for you. And Gijs van der Hoen asks, can you say something about the integration between Orocos and ROS control or some other control frameworks?
Yes, so there was some, so we are actually not using ROS control. I know that Jonathan Bourne, who was a big contributor also to the RTT-ROS integration, worked also very much with ROS control. There are some support packages to basically write ROS control or to use ROS control from within Orocos. But yeah, to my best knowledge nowadays, it's not supported by the latest version anymore. So yeah, I'm not sure what's the current state actually of this integration, but it was used in combination in the past and probably needs some polishing to make it work again. And on the ROS2 side, I'm not sure what the latest developments are on ROS control.
Okay, so this is possibly something for the community to explore. Yes, we have another question for Luca. Fuad asks, is ROS End Effector compatible with MOVEit? And how can it be integrated into MOVEit if it's not already?
Okay, yes, let's say it is compatible. We actually use MOVEit inside the ROS End Effector to actually look for pinches in the offline phases, but we don't use it, let's say, in a fully integrated way in our lab because the reason is that we use another Cartesian control framework that is a little bit different. It's called Cartesio, and it is real-time capable and works online. So that's why in the, let's say, for the Cartesian control, we use a different framework. So we didn't try to put ROS End Effector on top of MOVEit yet, but I believe it's possible, and they are fully compatible. So we will try out in the future if it's interesting for the community.
Okay, thank you. I think that was interesting to know as well. If I don't think we have any more questions from the viewers. So I actually had a question that I would like to ask Rafael. Perhaps I misunderstood this or I didn't notice this properly, but you did mention in the 6th slide of your presentation that shared memory is written on subscriber callback and shared memory is read during the publishers. I would imagine that it's the other way around, that subscriber callbacks would read shared memory. Could you maybe quickly explain something about this?
Yes, so the idea, the principle itself is a little bit contradictory if you first think about it. So your first impression is not a surprise, but the idea here, the underlying idea is that the module that we were seeing is the one actually providing the interface to the shared memory directly. So what's going on underlying the code is that this module is receiving a topic from a subscriber callback and receiving data from this topic. And what's happening under the hood is that it's mapping this structure and this information that is receiving to a structure that can then be instantiated into the shared memory to basically write this information to be able to be received by the Codesys. And the same thing goes on, or occurs on the other way around. So when we want to actually receive data from the automation side, what this module is doing is actually reading information from the shared memory and thus publishing it to a topic. So if your application were to plug to this module, the strategy would be reversed. So basically we would be subscribing to get the data and publishing to actually write the data, but under the hood and the module that is interfacing, the logic is a little bit reversed. Don't know if I explained it correctly, but yeah, it's actually easier to sense once you are actually trying out the things and doing the examples and seeing how the data is moving from node to node. But yeah, the idea is generally that. Okay, yeah, maybe like you said, if we look at examples, I get a better idea of this. We actually had another question as well from Arya. How fast is the cycle time and jitter that you can realize using Orocos plus ROS?
Sorry, was it for me? So could you
repeat
the question?
Yes, Johannes. It's regarding the Orocos. So I'll repeat the question again. How fast is the cycle time and jitter that you can realize using Orocos plus ROS?
So for now, I think we can, for the current ROS integrations are not focusing on real time. So basically, whenever we leave the Orocos domain, we don't consider it real time. We don't have the measurements in my head at the moment on how fast it is, but so I think, yeah, at the end, we just basically call in a non-real-time thread the ROS publishers for publishing. And of course, if the ROS subscriber callback is called, we actually forward it to an Orocos buffer and then eventually pick up the component that is reading the port. So there's some latency probably, but I'm not sure about the, yeah. So it's not meant to be to fulfill the real-time requirements for communicating between ROS and Orocos, only within Orocos. But that might change if we have a closer look at the real-time support of ROS2 itself, and then yeah, maybe we can integrate more deeply without extra threads to improve that.
Okay, thank you for the answer. I would actually like to look at the poll questions that we had posted and see some of the answers. Maybe they're interesting. So the first question that we had posted was, what barriers do you usually face to adopting a new tool? We had 16 votes, out of which 31% responded that they did not know that the tool existed in the first place. And if I was responding to this poll, I would have also picked this answer, to be honest. 29% responded that documentation was not very clear. 19% responded that installation and usage was actually too complicated. And another 19% responded that the tool was too specific or it was not applicable for them, or rather they would rather build their own tool in order to implement whatever logic they wanted to. So this is actually interesting to see that perhaps the biggest barriers for people, for users adopting your tool is that they should know it exists in the first place and that they should know how to use it in the second place. We also asked the question, are you familiar with or already using some of these tools or concepts? We had 9 responders, out of which 14% responded that they use ADA and ROS. Another 7% responded that they're actually using ROS End Effector. 36% responded that they're using Robin, and 43% responded that they're using the Orocos RTT. So I would actually like to ask all of the speakers today regarding the first question that we had, which is the barriers to users adopting your new toolkits or your new libraries. So the question I would ask each of you one by one, and since we have 4 minutes, maybe you can each take 1 minute to explain is, were you aware of some of these barriers? Do you think maybe there are other barriers? Did you actively try to overcome these barriers somehow, or in general, what would be your opinion? So could we start with Rafael, please?
Yes, sure. So we were very much aware of the fact that the major barrier to software application and usage is, in fact, people not knowing that the tool exists. And this was perhaps the main reason why we submitted our proposal to the ROS-I project, in the sense of trying to get a little bit leverage and visibility and dissemination into something that we were developing into this European project, scalable. So hopefully by doing that, and also by participating in events such as the one today, and we also have presented this last year, and we, in fact, we have been a presence and a assiduous presence to the ROS developers meetings, which I also would like to also kind of like invite the general audience to try to be more active in that front. By doing these kind of activities, hopefully we can raise awareness to what is being developed in the research ecosystem, and get more people to use these tools, which have this degree of innovation and novelty associated to that. Just to conclude, the second most voted part was the documentation. On that front, we also have expanded quite a lot since last year, specifically in our tool, to provide guides and usage information, not too extensive, but straight to the point and direct to the application itself, to actually make the life of developers wanting to integrate this kind of systems more, a more easy task to accomplish. So hopefully by doing that, we were able to somehow address some of the shortcomings and the entry barriers to new software, getting a track record in the community.
Thank you, Rafael. Alejandro, I would like to ask this question to you next. You already mentioned that ADA is something of a niche category in robotics, and perhaps these barriers make it even more difficult for RCLAda to be adopted. So what are your thoughts on this matter?
Yeah, thank you. Well, yes, it's true. We in the ADA world are used to being, we are really in a small position here. So actually in my laboratory, there are very few of us that use ADA, even me being a big advocate for it. So, well, I always try to direct people to success stories like the one that I linked in the presentation, where you can see that the technology is actually useful and it's not an all or nothing proposition, because you can use it for particular things like some software that's particularly interesting to prove some formal properties or things like that. So I'd say that's, but it's a hard fight for ADA for ADA users, because, and now with Rust is even harder.
Yeah, we're combining two niche categories into a super niche thing. It might be a bit challenging.
Some people say that ADA is more used than what is visible, because it's used in classified environments also. But well, I'm not really in that context, so I cannot say.
Okay, we're nearly ending, but Luca, could you quickly add anything else to this?
Yes, I believe that one of the barriers is represented by the lack of interoperability and lack of code reuse. This is especially true when we see that there is a gap between the lab and the technology transfer of the lab, either mechatronics or software to the industry. So what we try to do with ROS End Effector is to stress out the ROS standard as main, let's say, communication language in all the robotics application, especially for the industry. One barrier can be represented by the hardware, this for sure, the variability and so on. So I believe that going to abstract this kind of information and be able to give to the industry something that is really easy to use and fast to set up is the key. And for sure, this needs to work and does not need to give problems with maintenance time over time. So I believe that these are the open issue, and I believe that with what ROS Industry is doing, I believe it goes towards the right direction.
Yeah, so this is, I think, the purpose of ROS and FTPs, and I think we're getting closer to achieving this target. Johannes, do you have any closing thoughts on this issue?
Yes, for us it was very similar to what Rafael already said. So we also, I mean, Orocos is a quite old standard, and I think it was more known before all ROS came up. And with the ROS End project, we also, yeah, it was a big problem that the documentation was a bit spread between all the old web page and the GitHub wiki content and the ROS wiki. So one of the goals with the ROS End project was also to unify that and to add some more visibility again to Orocos, although ROS2 might catch up soon in terms of the capabilities. But we still think that Orocos adds values, and there are people who are interested. NASA works with it very intensively, for example. So we hope by doing this project, by putting this effort into Orocos again, that it's more widely known, and that people who can who have the respective requirements will consider to use it and then contribute to it in the future more.
Okay, thank you. So I thank all the speakers who've joined us today and presented some very interesting topics. I thank all the viewers who joined to the live stream. I hope you're all able to learn something interesting today, and I hope all your questions were answered. Thank you, everyone. And with this, we can conclude this session. Thank you.